Exam 2 is already on Moodle. It is in the practice exam folder and it is called information page exam 2. Okay? So if I'm you, I'll definitely print out that one when I'm doing the practice exam so that I know what exactly I have as situation, what I'm gonna give you, what you need to know, all of these stuff. So we're gonna start with an eye clicker on delta H of formation that we were talking about the last time. Which is the other method to calculate the delta HR other than the Hess.
Isn't it all added up equals 7?
So the question is, calculate the standard enthalpy of formation of C10H8. So knowing the fact that this is the reaction and this is the delta H of this reaction, and you're given those two delta H formation. So the question is to calculate the standard enthalpy of formation of C10H8. And I'm gonna stop it at 3 minutes.
B?
Yeah.
Yeah, and then O2 is 0. Yeah, so you know everything but C, so you just set it up a little bit. Yeah.
And this is a reminder that you can't use your laptop unless you are in the last 2 rows. So if you're not in the last 2 rows, please shut down your laptop. Or move to the last 2 rows, I don't mind.
Yeah, well, yeah, I would understand it.
Hold on.
Yeah, I didn't think like, cause like, I forgot.
Oh, it's products. There we go. That's the note.
Do you need some more time, guys? Yes, no? Okay, and by the way, you can always, if you change your mind at any point, you can send the new answer. And that iClicker can identify
It's minus X, right?
the last answer that you
Dark
clicked.
switch records.
So let's say you chose A and then you decided, oh, A is the wrong one, you click
There we go.
B, that would work.
Looks pretty good. Let's see if we just see one that makes one more. That's totally fine.
Great. I'm gonna stop it at 4, okay? And check 1, 2. I have 53% for B It's the most popular answer. It is the right answer, yet the percentage is not that high. And this is a question from the exam, and that's almost the percentage I get in the exam. So let's see what happened in here, although the percentage of such kind of question was 70 something on Fridays. Sorry, on Wednesdays. Okay. So first of all, we need to understand the question. The question is asking about the delta HF of C10H8. Okay? And you're given delta HR. In all the examples that we did before, we don't have delta HR, we're calculating delta HR. So it's just a slight difference in this question. So what I know that the delta H of the reaction equal to the sum of the delta H formation of the product minus, definitely taking into consideration the stoichiometric coefficient, minus Y of the delta H of all the reactants, all the products, all the reactants. So in other words, delta H0R, which is given to us in here, equal to the 10 times the delta H formation of CO2 gas. Why? Because it is a product and it is, the stoichiometric coefficient is 10, plus 4 times the delta H of water liquid, not the gas one, it's the liquid one, minus the delta H formation of the reactants, which is delta HF of C10H8 minus the delta H formation times 12 of oxygen gas. Now, the first thing, oxygen, the delta H formation of oxygen is 0 because it is in its elemental form, and the delta H formation of any element in its elemental form is 0. So that's 0. I know delta HR, it's given to me. I know delta H formation of CO2, it's given right here. I know the delta H of water, it's given here. So I'm solving for delta H of C10H8. Okay, what usually happens is you take your calculator and you begin punching numbers, doing it directly without writing the formula. And this is one of the mistakes that usually happens. So, minus 5156.1 equal to 10 times the delta H formation of CO2, which is minus 393.509, plus 4 times the delta H of water, which is minus 285.83 minus the delta H formation of C10H8. So you multiply this by this by that, and then move them to the other side of the equation in case you don't know how to solve one equation, one unknown. And then you calculate the delta HF. So you're solving for delta HF, and the delta H formation of C10H8 is B is the right answer, which is 77.7 kilojoule per mole. Okay? Now we're gonna do one more on also delta H formation and delta H, just to make sure that everybody get the idea before we move on to a new topic. Okay? I'm writing. Okay. Which of the following chemical equations corresponds to the standard molar enthalpy of formation of SO3? Okay, I'm gonna stop it at 110.
So what you want the molar enthalpy of whatever SO2, so it has to have on its outside one molar. Right? And so then you break SO2 up into its elements, which is S3. Which actually the sulfur is a special, so it's S3. And then O4 is the regular.
What was the other one? Sulfur and phosphorus?
So the only choice you can actually choose is like just like one compound.
Okay,
In
so
the
I'm gonna
last
stop it
example,
right
we
here.
had like two and two. We were just solving.
And check what you think. Send your answer if you did not yet. Okay. So I'm gonna stop it. Check what you think. And I have 64% for A. A is the right answer, but let's discuss why A is the right answer. First of all, I'm gonna start backwards, so I'm gonna start with D. D definitely is not the right answer because SO2 is a compound. We're asking about the standard molar enthalpy of formation. That means, by definition, it is the compound from its elements at their elemental form, in their elemental form. SO2 is not an element, so that's definitely not your choice. This is the first thing that you should eliminate from there. Now, between these two, this one is not obvious why it is wrong, but we talked about it before, that sulfur, we don't find it in nature as S. We find it as S8, and this is why I'm putting this question in here, just to bring your attention one more time, that phosphorus elemental form is P4, and sulfur elemental form is S8. So this one is wrong, because S we don't find it in its elemental form as S, we find it as S8. Between these two, this one is wrong because it has 8, and by definition, the molar enthalpy of formation reaction must be for 1 mole of SO3, not 2 or 3 or 4 or 8. It must be 1. And this is definitely balanced, so this is why we chose it. Okay? The same if I'm asking about H2PO4 and anything that have phosphorus, the elemental form of phosphorus is P4, not phosphorus PS. Okay? Now let's do this one. So write the balanced chemical equation for the formation of 1 mole of magnesium oxide. What is the standard enthalpy change for the reaction of 2.5 mole of magnesium with oxygen, knowing the fact that delta H formation of magnesium oxide is that much? So start writing the the formation reaction of magnesium oxide as the definition states, which is for 1 mole from its elemental form, from its elements in its elemental form.
I'm just gonna pick up the next. Because I don't know what else to do. And then I thought it could have been like 2,500.
So I'm gonna stop it at 350.
But why would you do that? Yeah, it happens at a yeah. Oh, that's a good thought.
That's a good thing. It didn't work out that way. It didn't do anything.
It would probably be that then. It's 500.
Are you not doing this?
I'm not sure.
Yeah. Sasha told me to do. Yeah. I did find it. We stuck it on the back.
Okay. 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 Let's see what's using. Very good. I have 79% for B. B is the right answer. That's very good. Okay. So let's see what is meant by this whole question. So first of all, it's asking me to write the reaction of formation for magnesium oxide. So magnesium oxide solid. So I know that magnesium belongs to group 2, so its elemental form, it's a metal and it's a solid in its elemental form. I know for sure that oxygen in its elemental form is diatomic, it's O2, and I'm gonna balance the equation to have 1 mole. So that's the reaction, the formation reaction. And it is given to me that this reaction, since this is the formation reaction, and this is delta HF, so the delta H for this reaction equal to minus 6.124 kilojoule per mole reaction. Okay? Now it's asking me what is the standard enthalpy change for the reaction if we have 2.5 mole of magnesium. So we said that it is dependent. It is amount dependent. All these delta H's, whether it is delta H reaction or formation, it is amount dependent. I know that I have 601.24 kilojoule per 1 mole reaction. But for each 1 mole reaction, I have 1 mole of magnesium. Now, if I have 2.5 moles of magnesium, how much is the, and we're gonna end up with kilojoules. So B is the right answer, okay? So here we're just kind of reminding you that the delta H formation is amount dependent. It's the same as delta HR as any delta H, as any enthalpy of reaction. Now, one thing that we didn't touch base on, we talked about Q. If Q is negative, that's an exothermic reaction. And if Q is positive, it is an endothermic reaction. So, in the exothermic reaction, we said that the reaction gives or releases energy. And at the molecular level, if we look at the reactants and the products, in any exothermic reaction, we always gonna find this is the energy or enthalpy. This is the energy. We find that the reactants have higher energy than the products in all the exothermic reactions. In other words, the products have less energy and they are more stable. So stable, less stable, more stable. More stable and have less energy. So in all the exothermic reaction, the reactants have higher energy. The opposite is true for endothermic reaction. For endothermic reaction, the reactants have less energy than the products. And this is why you need energy. You need to give the system energy to go from low energy to high energy to the products. In this system, the reactants are going from high energy to low energy products. So this is why the reaction releases energy. So you should be able, if you're given any graph, something like this. and it's the reaction coordinate versus the energy. You should be able to identify whether this reaction is endothermic or exothermic by looking at it. So these are the reactants or the energy of the reactants, and these are the products. So is this reaction endo or exo? It's an exothermic reaction because the reactants have higher energy than the product. So it's an exothermic reaction. Now let's take another example, which is again the energy versus the reaction progress or coordinate. Is that an endo or exo reaction? That's an endothermic reaction because these are the reactants, and those are the products. So you need energy to take the reactant from here to here, so it's an endothermic reaction. Okay, so we talked about delta H, about the internal energy in this chapter. We talked about the internal energy equal Q plus W. We talked about all of these, but we didn't mention how we're gonna calculate that. How we calculate delta H of the reaction? Okay, we know that we use Hess's law, but in the lab, how would you measure the delta H and the delta U, which is the internal energy? And this is what we didn't talk about. And to measure the delta H, which is the enthalpy of any reaction, we do our reaction inside a very simple device. It's called constant pressure calorimeter. It's mainly 2 coffee cups and a thermocouple or thermometer. And you put the reaction there, and you do the reaction and measure the temperature. And from the temperature, you can figure out the delta H. By definition, delta H is the heat at constant pressure. And this is why we measure, because we're putting this styrofoam thing or these 2 cups in the lab, on the bench. The pressure is not changing. It is the atmospheric pressure or the pressure of the room that we are inside, so that we can measure the delta H using this method. Now, the other method that we use to measure the internal energy, which is delta U, is using the bump calorimeter, which looks like something more complicated than the constant pressure calorimeter. So in this calorimeter, we put the sample, let's say, and this we usually use it. We put, for example, any compound that we have. We burn the sample in here. This is a steel bomb, and it is insulated from the outside. The water is there, and we have thermometer. The idea behind this is that it is at constant volume, and as you remember, delta U equal Q minus P delta V, where P delta V is the W. So if the volume is constant, that means V final minus V initial equal to 0. Okay, that's what does it mean, volume constant for this one. And if the volume is constant, that means the work is 0, which implies that the delta U equal Q, which is the heat. So the heat that we're measuring in this process equal to the internal energy. So the heat that we measured at constant volume, this is why we call it QV, constant volume, equal to the internal energy. So in other words, if I need to measure the internal energy, I use the bump calorimeter method. If I just wanted to calculate or to measure, not calculate, because in the lab we measure. If we wanted to measure the enthalpy, we use the coffee cup, the double coffee cup, constant pressure calorimeter. Okay? So that's the end of chapter 5. We talked about internal energy, about thermal equilibrium. It's a lot of topics that we talked about. I kind of, as everybody, figured out that I made the deadline for the homework of chapter 5, not this coming Monday, the Monday after, the 29th, I think, or the 25th or 29th, so that you practice more and you take the opportunity to practice more. If you're done from it, if you're done from chapter 5, because from the progress, I can see some of you already done from this. There will be another homework launched on chapter 6, and it's gonna be due the 5th of November. So that everybody in the class, if you're in a fast progress, you can start with chapter 6. If you want to master chapter 5, and I think it is a challenging chapter, this is why I gave you more time. And please don't use this kind of deadline that, oh yeah, I don't have to work on this until the day before that deadline. I gave you that much time to practice more and to be able to work more on chapter 4. Okay? And from here we're gonna start with chapter 6, which is more fun than chapter 5. Okay, so what we're gonna talk about in chapter 6? We're gonna talk about the structure of the atom. Where are the electrons? Where are the neutrons? Where are the protons? We're going to talk about the structure of the electron. Most of you know at least one of the theory that talks about, at least the Bohr theory of where are the electrons and the nucleus, and we talked about it a little bit in chapter 1. But guess what? For 2 lectures, we're going to get started with talking about light. Why would we talk about light in a chapter that talks about atomic structure? Isn't that weird for you that I say atomic structures and suddenly begin talking about wavelengths? I think everybody printed out. You find wavelengths, frequency, light, electromagnetic radiation. Isn't that weird to you? If I'm you, it will be weird for me. I'm sitting there, what's wrong with me? So why am I going to talk about light when I'm going to talk about atomic structure? Why am I wasting your time? Guess what? Most of the information that we learned about atomic structure and the structure of the atom, because we don't have a way kind of to look at, oh yeah, here are the electrons. We don't have this way. We don't have this technology. What we have is we understood the structure of the atom by, this is the atom, let's say, these are the electrons around it. What we do, or where are the electrons? We send light. The light interact with these electrons, and either it gives me another light, or it absorbs the light, or it emits another light, and from there, from what the atom is taking or giving as light, or as light is just a small kind of, the electromagnetic radiation, which is also the big name of under which all life is. So from that, from this interaction, we learned about the atoms. This is why we're going to talk for 2 lectures about electromagnetic radiation, because if you don't understand what is an electromagnetic radiation, you will have hard time understanding, okay, when I say, oh, this atom gives me that light, so that implies that the electron is here and it's going or jumping from this level to the other. So now what we're going to do today is fun. It's just introducing you to the light, to the electromagnetic radiation. Then on Monday, we're going to connect the dots from how electromagnetic radiation is to do with anything about the atom. So, what is electromagnetic radiation? As you sit in your apartment at home, like it or not, you're bombarded with all kinds of wavelengths. From the radio that are radio stations all around you in your area, that they are sending this electromagnetic radiation. It doesn't matter, you like it or not, you're bombarded with it. The only thing that sometimes you tune your radio to hear it, sometimes it's just bombarding you. The microwave, the TV, the cell phone, when it rings, when you're talking, it's all different electromagnetic radiation as you're sitting in your apartment, in your living room, having fun. Okay? Now, if you look to the picture that I have up there, can you see any difference between those radiations? Yes, please.
They're different wavelengths.
She's saying they have different wavelengths, and she means by wavelengths how the wave, is it a big wave, a small wave? Is it a small wave, a big wave, intermediate one? So this is the difference between one radiation and the other, is the wavelengths, okay? And this is let's identify the different wavelengths. The gamma radiation, which all of us know that it is a harmful radiation. That means it may harm us. It may even kind of break down the tissues. First of all, it have a very small wavelength, and I mean by wavelength is the distance between either two crests or two troughs. This is what is the wavelength. The wavelength of a gamma radiation is, we call it lambda, is 10 to the minus 12 meters. So we're talking about 1 picometer. It is the same size, that wavelength is the same size as atomic nucleus. Very short wavelengths, yet it is very powerful and very harmful for us as human beings. This is the gamma radiation. Now let's go to the X-ray, which I think everybody in this class know what is an X-ray. The wavelength of an X-ray, that means the distance between two crests or two troughs, is 10 to the power minus 10 meter. And all of us know that X-ray is harmful, but we take sometimes X-rays with some precautions. That's X-ray, and the size of the wavelengths is the same size as an atom. Okay? Now the ultraviolet ray wavelength, it's less harmful from X-ray and gamma ray, but at the same time it's still harmful. And this is why we wear sunglasses when we're out, because we want to preserve our retina from any harmful radiation. This is why you put sunscreen when you go. There is no beach in here, but when you're during the summer, when you're having fun in the pool, 10 to the minus 8, and this is the wavelengths, and the wavelengths of the ultraviolet is the same size of a DNA. Definitely it's harmful, but not as harmful as X-ray or gamma ray. Visible light is all what we can see as a human being. This is the lights, the colors, this is the visible region, this is all what we can do. And the wavelength is 10 to the minus 6 meters. Definitely it's not harmful. We can see the colors, it's not harmful. And the wavelength is the same size as a bacteria. Now infrared, some of the infrared, we don't see infrared. There is specially glasses to see infrared, but we can feel infrared. So if something is hot, that's you're feeling the radiation of an infrared thing. So it's called the thermal. Some part of the infrared is called thermal infrared. That means the one that we feel. The other part of infrared, we need special glasses to see infrared. And if anybody is in the army, they probably are trained to use the infrared, the night vision infrared. And the wavelength of that is the same as the pin tip, the size of a pin tip. And definitely the infrared is less harmful to us than the visible. That means less energy. Both of them, they aren't dangerous to us. Now microwave. The microwave is 10 to the minus 3. The wavelength is 10 to the minus 3. And it is the same size as dyes. Now the radio wavelengths, which is the radio, the long or short wavelength that you listen to your radio music, the wavelength of that is the same size, the same range as a mountain. That long is the wavelength of a radio. Okay? Now these are all the radiation. What we usually like to do as scientists is just squeeze them, all of them, in one spectrum, in one thing, and we call that the electromagnetic spectrum. And this is what the next slide is about, is to squeeze all of them in one spectrum, and it is called the electromagnetic spectrum. You need to know that the gamma radiation have the smallest wavelength. The smallest, as you remember, it was the same size as a nucleus of an atom in the picometer, yet it is the most energetic. Okay? And we're going to talk more about this in a minute. So what are all of these radiation that I talked about? All of these radiations, they have exactly, they were first talked about by Maxwell, and the idea behind all of these is that they have, we call them electromagnetic because they have an electric vector and magnetic vector. And those two vectors, as the wavelength is propagating, those two vectors are perpendicular to each other. And what I'm going to do is the following. I'm going to turn the lights, all the lights off for 1 minute, not more than that. Okay. And just so that you will be able to see. Okay. Okay, so what you see in here, can you see it, guys, or no? Okay, so as you can see in here, there is two waves, one in red, one in blue, and it's propagating. And this is what usually happens in electromagnetic radiation. It propagates, it's moved. And as they are propagating, there is a magnetic and electric vector to it, and it's moving, and they are perpendicular to each other. And this is why we call an electromagnetic radiation electromagnetic, because any electromagnetic radiation has this property. Okay? So let's go back. Sorry for anybody who get annoyed from on-off lights. Okay, so we'll go back. So whenever I tell you there is electromagnetic radiation by, or there is a radiation by default, it has those two vectors. Now, how we characterize a radiation? What is the difference between one radiation and the other? We just figured out that one of the differences is the wavelength. And by definition, the wavelength, we use the term lambda. And it is, by definition, the wavelength is the distance between two crests or two troughs. Okay? And this is a characteristic of any electromagnetic radiation. And usually, since it is a distance, it's either, sometimes we represent it in meter, centimeter, or nanometer. It's a metric measurement. It's meter, nanometer. Sometimes you would see it centimeter. So you would see it in more than one unit, but all of them metric. Now, the electromagnetic radiation, it has also another property, and that property is called frequency. And frequency, by definition, refers to the number of waves that pass a given point per second. Okay, I know that this definition makes no sense for most of you, and so I'm going to explain it in a minute. Usually, the term that we use for frequency is mu. It's not v. It's not velocity. I see sometimes some of you think that it's velocity. It's not velocity. It's not v. It's mu, and this is how we pronounce it, mu. And the frequency unit is either 1 over second, or second minus 1, or hertz. So when you hear, oh, that's that much megahertz or hertz, that means this is how much per second. Okay? So hertz is the same as second minus 1, or 1 over second as a unit. Okay? Now, what does frequency mean? Okay, so let's say I have those three wavelengths, A, B, and C, and let's say this is my start point. This line in here is my start point. So I start my timer for only 1 second. My timer is going to be set to 1 second. In this 1 second, I'm going to see how many crests going to pass through that line. And this is what's frequency. Frequency is how many crests going to pass through a line in 1 second. Okay? So let's say I started my timer. Which one would have a higher frequency, A, B, or C? What about doing it as an item? And I have just give me 1 second to get back to my amplifier and see
See?
Okay. which one will have a higher frequency, knowing the fact that frequency is how many crests gonna pass through that line per second? A, B, or C? And I'm gonna stop it at 50.
Yeah. I mean, there's always that one.
Yeah. It's like the other sounds are just like the other sounds or something
Okay, let's see. Great, C. C is the right answer.
Someone put E.
So the most crest that's gonna pass is in this one. What about the wavelengths? So which one? So you said that C, you agreed that C will have the highest frequency. Highest frequency. What about its wavelengths? The smallest. So just bring us to the next eye clicker. The bigger the wavelengths, the smaller the frequency, the bigger the frequency is independent of the wavelengths. What do you think? I'm going to stop it at 40. Okay, let's see. Very good. A is the right answer. So the bigger the wavelengths, the smaller the frequency. In other words, you're saying the wavelengths and the frequency are inversely proportional, not directly proportional. So if I tell you something have a high frequency, that's for sure low wavelength. The wavelength is short wavelength, okay? And that's bring us to the relationship between frequency and wavelength. So wavelength equals C over the frequency. So C is the speed of light in vacuum. Lambda, we just learned it's in a wavelength. And usually we put it in meter, especially when we use the C in meter per second. The frequency is 1 per second, or sec minus 1, or second minus 1. Now, the speed of light in vacuum equal 2.998 times 10 to the 8. This number will be given to you in the exams. Even this equation will be given to you in the exam, in the first page. Check the first page or information page on Midterms. Okay? So this is, if I have the wavelengths, I can calculate the frequency. If I have the frequency, I can know the wavelength. And this is the relationship between the two. Now, this is the electromagnetic spectrum in a better representation than the one that I showed before. As you can see, we have, in any electromagnetic radiation, you would have wavelengths and frequency. Okay? So the gamma radiation, which have the highest frequency, have the shortest wavelengths. I want everybody to see that they are inversely proportional in here. And the gamma radiation is the most energetic. So the highest energy is for the gamma radiation. X-ray has less energy than gamma radiation, but it has a shorter, a longer wavelength. So energy and wavelengths are also inversely proportional. So in other words, this is how the wavelength is increasing. And this is how the energy is increasing. So energy, and this is very confusing for most of the class, that we get to the end of the semester and some of you will still kind of confused what is the relationship between energy and wavelengths. When I say short wavelengths, that means high energy. Long wavelengths, that means small energy. Okay, they are inversely proportional. They aren't related to each other. They aren't directly proportional. So what do you need to know from this? You need to be able to construct this spectrum without
Violet, it's high
definitely
frequency.
any
High frequency.
any
Okay,
info there. So you need to know this is gamma radiation, then X-ray, then after X-rays comes the UV, then the visible. The red part of the visible gonna be in this side, the blue one or violet gonna be in this. And then below the visible I have IR, then microwave, then I have the FM, then the AM, that means both of them are radio frequencies. And you should know that this is the highest energy and lowest wavelength. So this is what you should be able to do. You should be able to construct this electromagnetic radiation and know which one is which and which has a higher wavelength or lower energy, higher energy. For example, the ultraviolet is higher energy than the visible. The IR is less energy than the visible. What about the wavelengths? You need to know all of these. Okay? Now, for the visible region, which is the only region that we can see as a human being, this is it's kind of expand that region. And I think most of you learned about this in high school, that the blue has the highest energy, lowest wavelengths. And usually you can use, okay. We're gonna get back to the visible region in a minute, but the red has the lowest energy, yet the highest wavelength, the longest wavelengths between the visible. Now, what is the relationship between energy and wavelength? So the energy equal hc over lambda. So this is the energy. H is a Planck's constant and will be given to you in the exam. C is the speed of light. It will be given to you during the exam, and lambda is the wavelength.
nice catch.
So if you know the lambda, you can calculate the energy. If you know the frequency, you can calculate also the energy. So the energy equal h nu. So there is two equations for the energy. Actually, one leads to the other. So the energy equal hc over lambda, and the energy equal h nu, which is the frequency. So if you have the frequency or the wavelength, you can calculate the energy. Okay? And definitely you need to keep it all in the same units when you're plugging in the numbers. So now for the visible region, the red, this is kind of summarized what we have: that red, orange, yellow, yellow, green, cyan, blue, violet, indigo, violet, and you can use this kind of acronym to keep it in your mind. I think most of you know this. So the red is the lowest energy, is the one with the lowest energy, and the highest energy is the violet one for that. And I'm gonna stop right here, and we're gonna start on Monday. We're gonna keep going with chapter 6 on Monday. Enjoy your weekend, and I'll see you Monday.